In the previous video, we walked through the process of taking every possible sample. Again, noting that we don't do this in practice, but the process or the theoretical exercise is useful because we can start to imagine or get a sense as to the distribution of where sample means will fall relative to our population. And two of the things that we came across was that the mean of the sample means is equal to the population mean when we consider all of the possible samples. And the other thing that we came across was that the sample means are smushed together. They're a little tighter of a distribution than we see with the overall population. Okay, and it's kind of hard to see in this example. It's not that much more tighter distributed, but this result holds true. And what we're going to talk about next is the central limit theorem, and that result, taking these two results to their conclusion, and that being the central limit theorem. So let me hit that button. Okay, so the central limit tells us if samples of a particular size, so in the previous video, we took a sample of size 2. If they are selected from any population, then the sampling distribution of the sample mean is approximately a normal distribution. And this approximation improves with larger samples. So that last little sentence, of course, our sample size of 2 is not a very large sample, and so the central limit theorem does not fully apply here. We're not going to get a nice, clean, normal distribution out of this type of situation. We also only have 10 possible samples, but when we think about expanding that and saying, 36 students, and we want to select 6. Right, let's say we're interested in the height of our class, and we have 36. Choose 6. Right, we just want to select 6 possible students. Here we have an n of 6, and again, the number of possible samples is quite large, so we won't walk through all of them. But what we know and what we can learn from the central limit theorem is that this distribution of all of the possible sample means that we could take is going to be a normal distribution, or approximately a normal. And so we can start to think about using our techniques with normal distributions in these situations, right? So in Chapter 7, we learn about normal distributions and how to calculate percentages or likelihoods of falling in certain areas of the normal distribution using our z-score and our z-table. We're going to be able to turn and use the same methods here because we're able to assume a normal distribution. And so we can know, okay, so we know we have a distribution of possible samples, sample means, and we can apply what we talked about in the last video, in that we know actually where this the mean of the sample means are. Right, we know where the center of this distribution is going to be. It's going to be the population mean. Okay, so again, we have a normal distribution, and we know we can describe a normal distribution, right? In the general sense, we want the mean and the standard deviation. For this case, we have the mean, which is the mean of the sample means, but it is the population mean. And then we do need to know the standard deviation. So that's going to be enough to describe this approximately normal distribution of these possible sample means. Again, we only take usually one sample, but it's going to fall somewhere within this distribution, right? So, okay, we choose 6 random people, and it turns out this time that it's, whatever value this is, or we took a different sample and it would be this value. Yeah. But knowing this normal distribution exists, we can get a sense as to how close we might be to the real population value. We can have a sense as to how unlikely certain extreme events might be. So this working with this normal distribution is where we're going to turn to in the next few chapters. But let's jump back and talk about this standard deviation. So how do we figure out what this standard deviation is? Well, what we know so far is that it's a tighter distribution than the population, right? So there's an underlying population distribution, and one of the important parts of the central limit theorem is that if you note, this hides behind it, but it says from any population, and what that really means is that we don't actually care what the distribution of the population is, and in fact, this works with normal distribution. So if the population is normally distributed, this works. If it's uniform distribution, it works. If it's any type of distribution, it can work. And so that's a pretty powerful result. So let me just I'm gonna pull up. It'll be easier to see using the text picture than me trying to draw all of these. So again, so noting that so if we look in the far left column, this distribution is kind of crazy. There's more value on the low and the high end and very little in the middle, right? We don't even have a normal distribution amongst the x's up top, or the the populations. We do have a uniform distribution in the third column, but all of these, if we take if we take all of the possible samples, right? So the sampling distribution becomes normal, especially when we have a higher value of n. Okay, so when we have n equals 2, like we did in our previous video, it stays a little funky, not quite a normal distribution. But you can see by the n equals 6, as we've been talking about in this case, we get pretty much a normal distribution. I mean, the one on the far right is still a little shady. We might want to be careful about drawing conclusions from that, but the other ones have a normal distribution, a typical feel, and you can see as n gets to 30, these are very classic normal distributions. And again, you know, we see samples with much larger values than that as well. So think about polling data. We've got hundreds, if not thousands, of phone calls made or contacts made. So yeah, and the other thing I would note is that the distribution, so if we look from n equals 6 to n equals 30 on all of these, the distribution gets tighter, right? So it's the same underlying population, but as our sample size increases, the normal distribution that we're talking about gets tighter. And that is an important result as well, in that as we take a larger sample, we get a better feel for potentially where that population value is. So as we move, you know, same population, but we have you know, n equals 10. If we increase that sample size, we're going to get a better or a tighter distribution. That's supposed to say n equals 20. It's hidden. That result is important, and in fact, thinking about this distribution, what we've been wanting is, what is this standard deviation? Well, it turns out that the standard deviation of the sample mean, so I'm going to call it sigma x bar with that subscript x bar, that is directly related to the population. Okay, so the how spread out the population is. So that's the population standard deviation, but we divide by the square root of n. Okay, and we won't get into deriving this equation in this course just for the sake of time, but as you progress in your statistics courses, you will most definitely if you continue, you'll definitely find out exactly where that comes from. But what we want to draw from that is that it's related to how spread out the data is, the population, right? So if you have a population that is more widely spread and you take a certain sample size, it's going to be more spread out than a sample from a population that's tighter. Okay, and that makes some intuitive sense. And then the second part is that as we increase n, which we've just seen, so if we increase n, then the standard deviation of the sample means goes down, right? And that's exactly what we see up here with as we increase the sample size, we get tighter and tighter. Okay. What else falls out from this is that this is not too hard of a calculation. And so, in fact, we can quite easily find the standard deviation of the sample mean. Now we have the information to describe this normal distribution that falls out of the central limit theorem. The one last word of caution I'll bring up at this point, because we are now talking about the standard deviation of the sample means, is that we don't always know this value, right? We don't always know the standard deviation of the population. Just like we've talked about that we don't actually always know the population mean. And in fact, oftentimes we don't, because that's maybe why we're taking the sample, right? We're curious about what do we think the mean height of our class is. Well, we don't know, so we're taking a sample mean. So in Chapter 8, we largely know these things, but as we move forward, or you may even be kind of pondering this and saying, okay, how do I know this value? Well, in practice, we often don't. And so we'll turn to methods in Chapter 9 as to how do we estimate these things, okay? And they're not, there's a pretty simple solution for estimating the population standard deviation. So if that's throwing kind of red flags in your head as far as understanding this whole sampling process and why we do it, that makes sense. So this is the standard deviation of the sample means, or another way to say that, or another term for that. So the standard deviation of the sample means. Or we use the term standard error. So I will often refer to it back as standard deviation of the sample means because it helps me remember, okay, what am I actually calculating here? But you'll hear standard error used quite often as well. So that's what the central limit theorem brings us, and we'll play around with that likely on Excel on Friday. But what we can see here is kind of the results of that, in that we get this normal distribution that we can play around with, and we can apply our normal distribution methods from Chapter 7, z-table, and so on. So we'll walk through some examples of that, but this is why we're going through the central limit theorem, is to get to this exact point where we can have some nice normal distributions, and we can start to cut these up and find probabilities between certain values.